Welcome to the deep dive. Today, we're doing something a little different. Our source material isn't, the usual articles. It's actually a set of chemistry exam questions.
Right, the questions answers the whole context.
Yeah, exactly.
And it might sound a bit like a revision,
Maybe.
but honestly, it's a great way to deep dive into some really fundamental chemistry. We'll be covering loads, energy, molecules.
Analysis, materials, even food production.
Exactly. The goal isn't just the answers, but understanding the why behind them, the core principles.
Think of it like a treasure map,
Yeah.
leading us to the key bits of knowledge. So, our mission today, unpack all that for you, give you that shortcut to getting informed on these chemistry topics.
Okay, let's dive in. Right. First up, the big picture. Energy. The sources start by looking at UK electricity generation, specifically the change between 2007 and 2017.
And there's a
Right.
really clear trend in the data presented. Over that decade, electricity from oil definitely decreased quite significantly.
Okay. And solar.
Solar saw a very noticeable increase. You can see the shift. So why move away from oil? The sources point straight to the environment, right?
They do. They lay it out pretty clearly. Burning oil releases carbon and it releases sulfur.
Oh.
The carbon becomes CO2, carbon dioxide. And the sources link that directly to, well, increasing global warming.
Right, and the sulfur.
That becomes sulfur dioxide, which is a major cause of acid rain.
Yeah.
Plus, if the burning isn't complete, you get carbon monoxide, particulates.
Nasty stuff.
Yeah, linked to smog, health issues. It's a whole chain reaction from just burning the fuel.
Which really explains the push for alternatives, like solar. The sources call solar more sustainable. Why is that the key distinction?
Well, the fundamental reason given is pretty simple. It's renewable. Oil, other fossil fuels,
Yeah.
they're finite. They'll run out. The sun, well, it's not going anywhere soon.
But it's not a simple swap, is it? The sources highlight some problems with solar, too.
No, it's not perfect yet. What's interesting are the practical hurdles. First, it obviously depends on daylight and the weather. No sun, no power, or less power anyway.
Except,
And the other big things mentioned are storage. How do you store that energy effectively for when the sun isn't shining? And the cost of the infrastructure needed to scale it all up.
Yeah.
Those are still big challenges.
okay, let's zoom in a bit. From energy down to the molecular level, the sources switch to organic chemistry here, specifically molecules called alkenes, and they provide data on boiling points. Comparing alkanes with different numbers of carbon atoms from 4 carbons up to 9.
Yeah, and if you look at that data, there's a definite trend. As you add more carbon atoms to the chain, C4, C5, C6, and so on, the boiling point generally goes up.
Right.
Quite significantly, actually, from like 0 degrees Celsius for the C4 alkane up to 151 Celsius for C9.
And that pattern lets you predict things, doesn't it?
It does. That's the power of seeing these structure-property relationships.
Yeah.
Based on that trend, you could estimate, say, the boiling point for the 7-carbon alkane.
Which wasn't listed directly.
No, but you'd guess it's somewhere around maybe 100 degrees C, looking at the pattern. The sources also kind of touch on why the graph might not be great for showing, like, a 3-carbon alkane,
Why is that?
simply because it's outside the range shown in that particular figure. The data set starts at 4 carbons.
Got it. Let's take a specific one. The C4 alkane butane. Its boiling point is 0 degrees C, according to the data. So what state would butane be in at, say, room temperature, 20 degrees C?
Well, if it boils at 0,
Yeah,
then at 20 degrees, it's already well past its boiling point. So it must be a gas.
as simple as that.
It really shows how boiling point tells you the physical state, based purely on that data provided.
And the C9 alkane, just for another example from the source, is called nonan, formula C9H20.
Right. And that fits the general pattern for alkanes, CnH2n plus 2. You can sort of see that formula emerging from the examples, even if it's not explicitly stated.
Okay.
And nonan's high boiling point, that 151 degrees C, that connects to another idea in the sources, fractional distillation.
Separating crude oil.
Exactly. Because nonan has a high boiling point, it stays as a gas for longer as it goes up the fractionating column. It condenses lower down, where the column is still hotter, compared to smaller alkanes with lower boiling points.
Because the column gets cooler higher up.
Precisely. Things condense when the temperature drops below their boiling point. Nonan needs it to be hotter to condense back into a liquid.
Okay, from structure to analysis, how do we figure out what's in a mixture? The sources look at paper chromatography, a common technique.
Yeah, it's a standard lab method. The material walks through the basics for finding an RF value, say for a dye. You draw a pencil line near the bottom of some special paper.
Pencil, important,
Yeah.
so it doesn't dissolve.
Right, put a spot of your dye on the line, then dip the paper edge into a solvent. Crucially, the solvent level has to be below the spot.
Okay.
Then the solvent travels up the paper by capillary action, and it carries the dye components with it, but at different speeds.
Separating them out.
Exactly. Then you measure how far the dye spot moved and how far the solvent front moved.
And that ratio, distance moved by dye divided by distance moved by solvent, that's the RF value.
It's like a fingerprint for that substance in that specific solvent.
Yeah.
It shows how it balances sticking to the paper versus moving with the solvent.
So the sources pose a scenario. Two students test the same dye but get different RF values. What's the likely reason given?
The number one reason highlighted is that they use different solvents.
And why is the solvent so critical?
Well, the solvent is the mobile phase. It's what moves. The separation relies entirely on the competition between the substance dissolving in the mobile phase and sticking to the stationary phase, which is the paper.
Ah, right.
Change the solvent, you change how well the dye dissolves or moves. That changes the balance, changes the separation, and boom, different RF value.
And just to be crystal clear from the sources, the stationary phase in paper chromatography is.
The paper itself, the source clearly states that. It's the bit that doesn't move.
All right, let's move on to material science. Polymers. The sources talk about polyethylene, polyethylene, and also polyesters.
Yep, polyethylene. Very common stuff. The diagrams in the source help show it's made by joining up lots and lots of small ethene molecules.
The monomers?
Exactly. The monomers, they link up to form these really long chains. The structure just shows that ethene unit repeating over and over.
Now, the sources mention a difference in how these polymers behave when heated, which is important for recycling. Why is polyethylene easier to recycle than thermosetting polymers?
Good question. Polyethylene is what they call a thermosoftening polymer.
Meaning
When you heat it up, it gets soft, it melts. So you can easily reshape it, mold it into something new. That makes recycling relatively straightforward.
Okay. And thermosetting ones?
They're different. When they're made, they form strong cross-links between the chains, a rigid 3D structure. If you heat them, they don't melt. They just degrade or char. So you can't just melt and reshake them easily. Much harder to recycle that way.
Got it. Now, you can get different types of polyethylene, right? How do the sources say scientists control that?
Yeah, the material points out you can tweak the production process by changing the reaction conditions. Things like the pressure you use, the temperature, or maybe the specific catalyst. Adjusting those lets you make different forms of polyethylene.
Leading to different properties, like HDPE versus LDPE, high density and low density polyethylene. Why is HDPE denser?
The sources give a really neat molecular explanation for that. In HDPE, the polymer chains are mostly straight, linear, so they can pack together very closely, very efficiently, like neatly stacked logs.
Right, compact.
Exactly. Yeah. In LDPE, the chains have lots of branches sticking out. That stops them packing closely together, more like a jumble of twigs.
Ah, I see. Less efficient packing.
Right. So same basic molecule, ethene, but that difference in chain structure, how they pack, leads directly to a difference in density. It's a nice link between structure and property.
The sources also bring up functional groups when talking about making polyesters. They ask about identifying an alcohol group.
A functional group is like a specific bit of a molecule, a particular arrangement of atoms that gives the molecule its characteristic chemical behavior. It determines how it reacts.
Okay.
And the alcohol functional group, the one identified in the source, is the SOH group. Oxygen bonded to hydrogen, attached to a carbon chain. You find it in ethanol, butanol, things like that.
And for polyesters made from reacting different monomers together, the sources mention something else is produced too.
Yeah, they point out that when the monomers join up, whether it's monomer A with B or A with C in their examples, a small molecule is also formed.
And that molecules?
Water, H2O.
Okay.
This is typical of condensation polymerization. The monomers link up by eliminating a small molecule, often water, in the process.
Okay, next topic. Fertilizers. Super important for agriculture. The sources introduce NPK fertilizers, containing nitrogen, phosphorus, and potassium.
Yep, the big three nutrients plants need for healthy growth. N, P, and K. And the source material lists some specific chemical compounds. It asks which ones provide two of these essential elements.
And those are
ammonium phosphate that's got nitrogen from ammonium and phosphorus from phosphate, and potassium nitrate that's got potassium and nitrogen from nitrate.
right.
It's interesting, isn't it, how chemists combine different elements into compounds to deliver exactly what the plants need. Tailor-made plant food? Kind of.
The sources say these fertilizers often start from rocks containing calcium phosphate. What happens when you react that with acids?
Well, the calcium phosphate in rock isn't very soluble in water, so plants can't easily absorb the phosphate.
Ah,
So the sources say reacting it with nitric acid produces calcium nitrate, which is soluble. And reacting it with phosphoric acid makes another soluble calcium phosphate compound, sometimes called calcium hydrogen phosphate or similar.
the key is making it soluble.
Exactly. So the phosphorus can dissolve in soil water and be taken up by the plant roots.
Now, the sources compare two ways of making ammonium sulfate, another fertilizer. Industrial scale versus lab scale.
They describe them quite differently. The industrial method is presented as continuous. It just keeps running, it's fast, makes large amounts, and the product is collected continuously.
Okay, sounds efficient.
Yeah. The lab method, though, is a batch process. You do it one reaction at a time, maybe in a beaker or flask. It's described as slower, better for making smaller amounts. And it involves distinct steps, like heating to evaporate water, cooling to crystallize, filtering, then drying the crystals. More hands-on steps.
So if you look at the trade-offs suggested by those descriptions.
Well, the industrial way is clearly about speed, volume, efficiency for mass production.
Right.
The lab method gives you maybe more control over things like purification through crystallization and filtration, better for smaller quantities where perhaps purity is key, or you're just demonstrating the principle. It really highlights how the scale and purpose change the approach.
Let's jump back to organic chemistry, but with a twist. Cycloalkenes.
Ring structures.
Exactly. Ring-shaped hydrocarbons, and the sources point out they also have a carbon-carbon double bond somewhere in the ring.
Right. And the classic test for that double bond, COC, is described in the sources.
The bromine water test.
That's the one. You add bromine water, which is normally orange or brown. If there's a CC double bond present, the bromine reacts with it, and the color disappears. It goes colorless. Simple visual test.
The sources give us a few formulas. Cyclobutene is C4H6, cyclopentene C5H8, cyclohexene C6H10. Can you see a pattern there?
Yeah, if you look at the relationship between carbon and hydrogen atoms, for N carbons, the hydrogens are 2N minus 2 fun. So the general formula is CnH2n2.
CnH2n2. How does that compare to, say, normal alkenes or alkenes?
Well, a normal alkene with one double bond, no ring, is CnH2n. An alkane, no double bond, no ring, is CnH2n plus 2. So compared to an alkane, the cycloalkene CnH2n2 has 4 fewer hydrogens.
Okay.
2 hydrogens are lost because of the double bond, and another 2 are lost because the ends of the chain join up to form the ring. So the formula reflects both features.
Clever. They also show a reaction example, chlorine reacting with cyclohexene.
Yeah, the diagram in the source shows what happens to the chlorine molecule, Cl2, adds across the double bond.
Breaks the double bond.
Breaks the double bond, yep. And one chlorine atom attaches to each of the carbons that were part of that double bond. So C6H10 becomes C6H10Cl2. It's a typical addition reaction.
And from that product, C6H10Cl2, there's a calculation.
Calculating the percentage by mass of chlorine in that molecule.
How do you do that?
It's standard procedure, using the relative atomic masses they provide, H1, C12, Cl35.5. First, work out the total relative molecular mass of C6H10Cl2. Add up all the atoms. Then find the total mass just from the 2 chlorine atoms, 235.5.
Okay.
Then divide the mass of the chlorine by the total molecular mass and multiply by 100 to get the percentage. The source guides you to an answer around 35.5% and stresses showing you're working.
Right. Shifting back to analysis, identifying ions. The sources look at a compound called potash alum, KLSO42. How do you test for the potassium ion, KIO, according to the material?
Potassium's a group 1 metal, so the classic test described is the flame test.
Flame test. Okay.
You put a sample in a flame, and potassium ions give off a very characteristic lilac color. That's the identifier.
And if you needed something more quantitative, maybe measure concentration.
Then the sources point towards an instrumental method.
Yeah.
Flame photometry. It also uses the light emitted in a flame, but it's much more precise. It can identify the element and measure how much of it is there.
Okay. Now, what about the other metal ion in potash alum? Aluminum allo. The test involves adding sodium hydroxide solution. What happens first?
Initially, adding sodium hydroxide, NaOH, causes a white precipitate to form.
Why?
Because the aluminum ions, Al, react with the hydroxide ions from the NaOH. They form aluminum hydroxide, LH, which doesn't dissolve in water, so it appears as a white solid.
But the sources suggest other ions might also give a white precipitate with NaOH, so how do you confirm it's aluminum?
This is the crucial next step described. You add more sodium hydroxide. Add it in excess.
And what happens then if it is aluminum?
If it's aluminum hydroxide, The precipitate dissolves again in the excess strong base.
It dissolves. Why?
Because aluminum hydroxide is amphoteric. It can react with acids and strong bases. So the excess OH reacts with the LOH precipitate, forming a soluble complex ion. That dissolving in excess AOH is the key conformation for aluminum, distinguishing it from other metal hydroxides that might precipitate but don't redissolve.
That's neat, a multi-step conformation.
Exactly. It's vital for accurate identification, ruling out false positives.
Okay, one more ion in potash alum, sulfate, SO4. How did the sources say to test for that?
For sulfate ions, the test described involves adding two things. Dilute hydrochloric acid, HCl first, and then barium chloride solution, SO.
The acid first, then barium chloride.
Right. If sulfate ions are present, you get a white precipitate forming. That's barium sulfate, BSOEO, which is very insoluble.
And why add the acid first?
That's important. The HCl stops other things, like carbonate ions perhaps, from precipitating with the barium chloride. Carbonates would also form a white precipitate, barium carbonate, but they react with the acid first. So if you add acid, then barium chloride, and still get a white precipitate, you can be confident it's sulfate.
Let's switch to metals again, but think about sustainability. Copper and alloys. Solders, for instance. The sources show different solder compositions. Solder A has tin, copper, lead. B and C have tin, copper, silver. And there's a big health reason given for preferring B and C over A now.
Absolutely critical reason. Solder A contains lead. And lead, as the source implies, is toxic. A heavy metal you don't want leaching into things, especially electronics or plumbing.
Right, so that's why the shift to lead-free solders like B and C.
Exactly. It's a clear case where chemical composition directly impacts health and safety regulations.
But interestingly, B and C both have tin, copper, and silver, yet the sources show they melt at slightly different temperatures. One at 228 degrees C, the other 217 degrees C. Why the difference?
The explanation given in the source is that they have different compositions or structures.
Meaning?
Even though they use the same metals, the percentage of each metal is likely different between solder B and solder C. Or maybe the way the atoms arrange themselves in the solid alloy structure is slightly different. And even small changes in composition or structure can have a noticeable effect on physical properties, like the melting point, which is obviously really important for a solder cap. You need it to melt at the right temperature for the job.
Makes sense. Now, thinking about copper itself, sustainability comes up. Recycling versus mining new copper. What benefits of recycling are highlighted?
The sources list three main advantages. One, it conserves natural resources. We don't deplete the finite copper ore in the ground.
Okay.
Two, it uses much less energy.
Yeah.
Getting copper from ore is very energy intensive. Recycling takes far less.
It's saving.
Huge. And three, less pollution and waste. Mining and processing ore create a lot of waste rock and potential pollution. Recycling avoids much of that. So clear environmental and resource benefits according to the source.
The sources also mention a really interesting alternative for getting copper from low-grade ores. Phytomining.
Yeah, that sounds pretty cool, doesn't it? Using plants.
How does it work?
The process described is you grow specific plants on soil that has copper in it, but maybe not enough to mine conventionally.
Yeah.
These plants absorb the copper ions through their roots as they grow. They accumulate it.
Okay.
Then you harvest the plants, burn them to ash. This concentrates the copper that was spread throughout the plant into the ash.
And then you get the copper from the ash.
Exactly. Extract the copper compound from the ash, then process that to get the metal. It's a biological way of concentrating the metal.
Fascinating. So why isn't it used more widely if it's so clever?
The sources give two main drawbacks. First, it's slow. Plants take time to grow and absorb the copper.
Right.
And second, the amount of copper you get, the yield, is typically quite small compared to industrial needs. So while it's an innovative idea, especially for contaminated land maybe, the sources suggest it's not yet practical for large-scale copper production due to the speed and yield limitations.
Yeah. Okay, let's dive into our second to last topic, kinetics, reaction rates. The sources use the reaction between zinc metal and sulfuric acid as an example. You measure the hydrogen gas produced over time.
Right, a common experiment. The setup shown uses a flask for the reaction and a gas syringe to collect and measure the volume of hydrogen gas evolved. And the sources cleverly point out a potential practical error.
What's that?
The diagram might show the gas syringe isn't properly sealed onto the flask. There's a leak.
Ah, so the gas escapes.
Exactly. If it's not sealed, some or all of the hydrogen produced just leaks out instead of going into the syringe. That would mess up your measurements completely. You wouldn't measure the true rate or the total volume. Good experimental technique is crucial.
The results are shown on a graph, volume of gas versus time, and the lines on the graph eventually level off, become horizontal. Why does that happen?
That flat line means the reaction has stopped. It's complete. Yeah. One of the reactants, either the zinc or the sulfuric acid, whichever runs out first, has been completely used up. So no more gas is being made, and the volume in the syringe stops increasing.
How does the graph also show the effect of acid concentration? There are lines for different concentrations.
You can see it clearly. The line for the lower concentration acid is less steep than the line for the higher concentration.
Less steep means.
Slower reaction rate. The gradient or slope of the line represents the rate of gas production. Flatter slope, slower rate. Also, if the acid concentration was the limiting factor, the graph shows the lower concentration produces less total gas in the end. The line flattens out at a lower volume.
Got it. There's also a calculation task. Find the reaction rate at a specific time, say 80 seconds, for the lower concentration curve.
Right. The source expects you to use the graph. You typically find the volume of gas produced at 80 seconds on that curve. Then you'd calculate the rate, often as volume time for the initial part, or maybe by drawing a tangent at 80 seconds if the curve is, well, curvy by then. The source specifies giving the answer to two significant figures.
And showing you're working.
Always important. Show how you got the numbers from the graph. It's about interpreting that graphical data.
Finally, catalysts. The sources say adding a certain metal ion can speed this reaction up by lowering the activation energy. Which ion and why?
The ion identified in the source is cuose, the copper-2 ion.
Copper. Why copper?
Because copper is a transition metal. And transition metal ions are well known for often acting as catalysts in various reactions. They can provide an alternative pathway for the reaction that requires less energy to get started, lower activation energy.
Okay, final section. We're back to organic molecules, focusing on ethene, ethanol, and butanol relevant to fuels and chemicals. Ethene, where does that come from initially, according to the sources?
It comes from larger hydrocarbon molecules, the ones you get from fractionally distilling crude oil, long carbon chains.
Right. And how do you turn those large molecules into smaller, useful ones like ethene? What's the process?
That process described in the sources is called cracking.
Cracking, like breaking them.
Essentially, yes. Breaking long chains into shorter ones. The sources specify the conditions needed. High temperatures, around 600 to 700 degrees Celsius, often with a catalyst like a zeolite catalyst to help it along.
Okay. Now, you can make ethanol from ethene by reacting it with steam. The sources say this reaction is exothermic, it gives out heat.
Yeah.
How are the conditions chosen to make this process work economically?
This is a great example of chemical engineering principles from the source material. It's all about compromise. Because the reaction is exothermic and reversible, a low temperature would actually give you the highest yield of ethanol at equilibrium. But low temperature means a really slow reaction rate. Not practical.
Right, too slow.
Then pressure. The reaction goes from two gas molecules, ethene plus steam, to one gas molecule, ethanol. So high pressure pushes the equilibrium towards the product side, increasing yield.
So use high pressure.
But high pressure means expensive, strong equipment, and potential safety issues. Big costs.
So it's a balancing act.
Exactly. The economic conditions described are a compromise. A moderately high temperature and pressure that gives a decent yield at a reasonably fast rate without the costs and dangers becoming prohibitive. Balancing yield, rate, and cost safety.
The sources mention another way to make ethanol too, from sugar.
Yep, that's fermentation. Using yeast to convert sugars into ethanol. An ancient process, really.
And similarly, butanol can be made from sugar, but using bacteria this time. Based on the comparison to fermentation, what conditions would be likely?
Well, following that comparison in the source, you'd expect similar conditions to yeast fermentation. Probably warm temperatures and definitely anaerobic conditions, meaning no oxygen allowed, as the bacteria that do this often work without air.
Makes sense. There's also a calculation involving ethanol as fuel, burning it in a car. If you know the energy needed per distance and the energy released per mole of ethanol, how many moles for a 200-kilometer trip?
The source guides the calculation. First, find the total energy needed. Multiply the distance in meters, usually, by the energy used to meter.
Okay, total energy.
Then take that total energy and divide it by the energy you get from burning 1 mole of ethanol. It's enthalpy of combustion.
Energy needed divided by energy per mole gives moles.
Exactly. And following the numbers in the source, the answer comes out as 300 moles of ethanol needed for that journey. It connects the chemistry to a real-world scenario.
And just to wrap up the chemistry, the sources provide the equation for the complete combustion of butanol.
Right. The balanced equation given is CHEROH plus 6CROs goes to 4CO plus 5HO.
Butanol plus oxygen gives carbon dioxide and water.
Assuming complete combustion, yes, those are the standard products.
Wow. Okay, we started with, well, what looked like homework. And we've actually covered an incredible amount of ground.
Yeah.
Seriously, energy sources, environmental impacts.
Molecular structures, alkanes, polymers.
How to separate things with chromatography, identify ions with tests.
Making fertilizers, getting metals, even using plants for phytomining.
And reaction rates, catalysts, making fuels like ethanol. It's all in there.
It really is. And it shows how all these topics in chemistry are, connected. Understanding the details we pulled out, like why polymers have different densities, or the steps in an ion test, or the compromises in industrial processes that's key to understanding the world. Materials, energy, the environment.
Yeah.
The sources did a good job moving from the basics, like functional groups, right through to practical uses like fuels and fertilizers.
It's amazing how much is packed into questions designed to test those fundamentals.
Well, thanks for joining us on this slightly unusual deep dive today. Hopefully it helps you see chemistry not just as facts and figures, but as this, fascinating way of figuring out how stuff actually works. Definitely. And maybe a final thought, drawing only on everything we've just discussed from these sources. We looked at so many different ways of doing things, didn't we? Industrial cracking, lab synthesis, fermentation, flame tests, phytomining. It really reveals chemistry isn't just about knowing things. It's about this constant search for the best way, the most efficient or sustainable, or maybe just the most suitable way to transform materials and energy to get what we need. And every single method we touched on came with its own set of, challenges and trade-offs. Speed versus yield, cost versus safety, new ideas versus established ones. So thinking about all those different approaches we uncovered, what stands out most to you about how scientists and engineers actually go about achieving these chemical goals?